Hello again, and in this section we're going to look at what the AC characteristics of a scope probe are. And this is where we need a higher performance signal generator to demonstrate this, because we need to go up into tens of megahertz. So from an AC perspective, let's have a little look at what's going on here. So we're going to look at the TA386 probe from an AC perspective in ×1 and ×10 mode. But before we do that, we need to discuss capacitive reactance, which is XC. Now, level 1 at university, you'll probably come across reactance. And because oscilloscope probes primarily are trying to get the capacitance down to a very, very small value, so they actually don't have significant effects on your circuit, then we need to actually understand what reactance is and how it's calculated. So here we have a variable frequency sine wave generator, and here's my capacitor, and the formula for reactance XC is equal to 1 divided by 2 pi FC, where F is in hertz and C is in farads. Now, just as an example, if F was 10 megahertz and C was 50 picofarads, then the reactance is 318 ohms. Now, this 50 picofarads here is not actually that dissimilar from the capacitance in a scope probe that we're actually using. It's probably a bit less than that, actually. But anyway, the bottom line is that this reactance is actually quite low, and this is actually the load on the signal that's being generated. So whereas before in DC we were looking at tens of mega ohms when you use our ×10 probe, in this case we're actually, because the higher the frequency goes, the more the reactance becomes significant within the circuit, and this actually does cause problems and does load circuits. But it's common to all all probes and all scopes. Okay, so the battle with the design of scope probes is trying to minimize this so that you don't interfere with the signal you're trying to monitor. So let's also have a look at something else, because we also need to look at bandwidth. We know that from the specification of this probe that we're working with that at ×1 it has a bandwidth of 10 megahertz, and at ×10 it's got a bandwidth of 200 megahertz. Now I can't go anywhere near 200 megahertz in this experiment. However, I will be able to show you some interesting effects. So the bandwidth is defined by basically the frequency range for which you maintain a Vmax through to 0.707 of Vmax. So ideally, what you end up with this kind of characteristic. Now, this is a characteristic for a low-pass filter. Here we have Vmax. We want this as constant as possible for our frequency range. We don't deviate our signal. We don't change our signal in any way throughout the range of the frequency bandwidth of the probe until you get towards the end, of which we get to the 3 dB point, which is max times 0.707. And that gives our 3 dB point, which is the bandwidth point of our frequency range. And that's how we get the bandwidth. So here's DC down here, 0 hertz, and up here, for our ×1 probe, we'd expect that to be around about 10 megahertz. And on the ×10 setting, we'd expect this to be around about 200 megahertz. But let's actually see what happens when we do this for real. So here we have the TA386 in ×1 mode, and what I've done here is I've shown you the capacitance. This is a very simplified schematic of what's going on, but we adjusted the capacitance of our probe by tuning it right at the start of this presentation. And so what we now have is a 2-volt peak-to-peak signal generator doing a sine wave, going to our probe tip, and we've grounded it, goes through this to our picoscope. So let me just show you what I've done in reality, and if I can change my screen over. So there we have our picoscope here, channel A with our TA386 probe, and it's connected to the signal generator lead. So this is my ground of my signal generator, and this is the output of the signal generator going to my hook probe. So that's my circuit I've got. Now, I'm not going to show you the signal generator because you don't need to see it. What's more important is actually what it's actually doing in terms of the signal generation. So let me now change my screen over and go to the picoscope. So here we have the picoscope, and what I've done is I've set it up so that we can see the peak-to-peak voltage, which you can see it's actually sitting around about 2 volts. And I'm also displaying the frequency as well. So I've found these parameters through the measurement facility here. So this is from the measurement. But what I'm really interested in here is the peak-to-peak voltage and what's happening with that, and also the time base, so I can see this signal and you can see what's going on. So I'm not going to split my screen this time, because what's really interesting is when I change the frequency on my signal generator, you'll see this change, and equally you'll see the display change. But what we're interested in was what's happening with this peak-to-peak voltage. So at the moment we have 1 kilohertz. So I'm now going to change that frequency to 10 kilohertz. I've recorded this value here at 2 for my tabulated results. And if I now go to 10 kilohertz on my signal generator, whoops, let me just go to the time base here, change that to, oh, I put in the wrong number, that's why. We've got 10 kilohertz now, and you'll see that that number of around about 2 volts hasn't changed. That's really good. It's looking great. So now I'm going to change this again to 100 kilohertz. And now we're on 100 kilohertz. I'm going to change my time base to so that it extends this signal. We're on 100 kilohertz, and you'll see once again this hasn't changed, which is absolutely fantastic. So we're getting that very, very good linear response. And so now let's change it to 1 megahertz. And now we've got 1 megahertz, and once again this peak-to-peak voltage hasn't changed. So it's a very, very good linear result. And we're on 1 megahertz. Now let's go to 10 megahertz and see what happens. So we go to 10 megahertz. Here we're on now 10 megahertz, and now you'll see our peak-to-peak signal has now dropped. So it's now 1.326. Let me just open this up a little bit. And if I now go to the maximum range of my signal generator, which is 20 megahertz, I'm just going to put in 20 megahertz here and put that in. And you'll see it's now 20 megahertz, and you'll see the signal's dropped again to around about 0.8 volts. So what would be really interesting to see is actually what the bandwidth is. So if I try and find the number of which this is around about 1.414, which is the 3 dB point, then we can actually get an idea of what the bandwidth is. So I'm going to slowly change the frequency, and let's see, there we go, 19. And what I'm looking for here is the point at which this gets to 1.414. So we're slowly going up here, so I'm slowly increasing decreasing the frequency. So it's around about sort of like somewhere between there. So it's about 8.7 megahertz. Now remember, the bandwidth of this probe when it's in ×1 mode is meant to be 10 megahertz, but that bandwidth is actually dependent on how you tuned your probe in the first place. So we tuned it to try and get a square wave. And so there's an argument to say that if you don't adjust that quite right, then the bandwidth will be slightly either higher or lower, depending on what that final capacitor was set to. So this is why we're getting a slight discrepancy between the bandwidth that's actually recognized here against the bandwidth that's stated in the datasheet. But that doesn't make it wrong. It's actually just the way we set up the capacitor. So let me now go back to our PowerPoint. And so what I did was I tabulated those results, and these are ones I did earlier on before I started doing this particular presentation, just to see the numbers. And we got around about 9 megahertz for the 3 dB point. So it's not far out, but that is actually because of the adjustment of this capacitor in here. So what can we say about all of this? Well, the capacitive reactance XC is 1/2 pi FC. And what we're saying is that the capacitance of this probe is in the tens of picofarads, and this is defined in the specification of the probe. And therefore that means that when you put these figures into here, you end up with hundreds of ohms is the reactance, the capacitive reactance. And therefore this becomes so significant in relation to this 1 meg component that in fact the capacitance becomes dominant at high frequency. And so the loading of this setup on your circuit becomes actually quite significant. And so you've got to be careful when you're using ×1 probes for high frequency work, not only because of the restriction of the bandwidth anyway, but because of the reactive component that's actually in there as well. So what we're now going to do is look at this from a times 10 perspective. So let's go to the times 10, and here's the circuit for the times 10. And what I'm going to do here is move to my picoscope, and I'm now going to change my probe to times 10. So I'm just switching that over. Probe now goes on to times 10, and I'll just change this back to plus or minus 2. There we go. And I'm just going to put this signal back down to 1 kilohertz again, so that we can see it. I've just got to change my time base back to something we can see, and there we go. So once again, we've got our, this is now on times 10. We've now got a 2 volts peak to peak back, and we've got a frequency of 1 kilohertz. So once again, I'm going to start raising the frequency. So I'm now going to go to 10 kilohertz and enter that. Here we got 2 volts. This hasn't really changed much. We've got 10 kilohertz. Let's go to 100 kilohertz and change this so that we can see our waveform nicely there. This has actually risen a little bit, which is rather interesting, just a little bit, but we're on 100 kilohertz. I'm now going to go to 1 megahertz and change this again, so 1 megahertz. And so this is actually, around about 2.04, not dissimilar to the last reading at 100 kilohertz. So we're now on 1 megahertz. Now let's change that to 10 megahertz. And I'm just going to open up my time base here. There we are. So 2.08, this is actually just slightly increasing, not a huge amount, but just a slight increase. And this is now on 10 megahertz. And now let's go to 20 megahertz, which is the limit of my signal generator. And you'll now see that this has actually gone up to 2.15 or 2.13-ish volts at 20 megahertz. But let's have a look at this tabulated. So let's go back to our presentation. And once again, I did these numbers earlier on. So these numbers you get. So why are these numbers actually rising? It's good that they're actually relatively linear. So we're not getting a massive drop at the higher frequency, which is great. So this is just going to show that our probe does have a higher bandwidth than the previous example when it's in times 1 mode. However, this is changing. And what's actually going on is that this is becoming a tuned circuit. And this is where you get into the complexity of oscilloscope probes. You've got capacitance, you've got inductance, you've got the lead that's actually connected between your signal generator. There's reflections in the line at higher frequency. And this is where you get into transmission line theory. And this is way beyond what we're trying to do here. But this is where the price of probes makes a massive difference, because what the manufacturer are attempting to do is trying to make this as linear as possible. And so that, what you see here at this point is actually what you're measuring there, and it's not influencing the circuit in any dramatic way. But this is also why really high performance probes cost so much. So as I said, this is about understanding the limitations of the test equipment, looking at what you're trying to measure, and really educating you on the fact that you have to be aware of all of this stuff, so that you know where all the limitations lie. And the more you understand about this, and the more you know, then it means that when you come to test and measurement, then you're actually doing it from a place of knowledge, not from a place of, I'll just stick this probe on here and see how it goes. It's about truly understanding what's happening, okay? So let's have a look at the next bit here. So given that all what we've discussed, why do we have ×1 probes? Because it seems to me as though ×10 is the best probe to use. Well, there is actually one primary reason for using ×1, and that's all to do with measuring small signals. Now, when you in a picoscope, when you select ×10, then the minimum vertical scaling range is actually plus or minus 200 millivolts. Whereas when you're in ×1, the minimum is plus or minus 20 millivolts. So that means that using a ×1 on low signals, you're actually able to examine the signal in more detail. I just want to show you that so that you're aware. So let me just turn my signal generator off a minute. That's off. So if I look at my that's not the time base, there we go, the voltage range. Now this is on times 10, and you'll see this is plus and minus 200 millivolts. But if I change my probe to times 1 and then look back at the vertical, you will see that's now changed to plus and minus 20 millivolts. So it allows us to actually examine smaller signals when we actually have a times 1 probe, because we haven't got the attenuation. So it does like make sense. So that's primarily the reason for times 1. So one slight final thing about what you see is not necessarily what is actually happening. Because why do high frequency square waves sometimes look more like sine waves when observed on a scope? And there's a really, really good reason for this. So a square wave in the frequency domain is constructed from the mathematical addition of a series of sine waves based on the fundamental and all the odd harmonics. So if we have a 1 volt peak to peak 10 megahertz square wave, then and they're all sort of, and what happens is you get the addition of all the phase lock waveforms that are actually of the odd harmonics. So we've got the 1 volt at 10 megahertz is our fundamental. Then you've got 1/3 at 30 megahertz, and 1/5 at 50 megahertz, and 1/7 at 70 megahertz, etc., etc., etc. And what that looks like is this. So here you have a square wave, but actually it's made up, the square wave in the frequency domain is made up of a series of sinusoids, of which the fundamental is there. So this, for example, is a 10 megahertz, but then this one is a smaller 30 megahertz. This one is a smaller 50 megahertz. This one's a smaller 70 megahertz. And this one's a smaller 90 megahertz. And what happens is when you start to add all these waveforms together on the basis they're all phase locked, then there's your fundamental. But when you add this to that, then you end up with this kind of waveform, etc. And what this means is that if you are bandwidth limited, then you may well have a square wave at your signal source. But if the bandwidth is limited by your scope probe or the actual scope itself, because the scope, the picoscope one I'm using here has got 100 megahertz bandwidth, so we can't see frequencies actually at a higher range. So we actually start to eliminate these higher frequencies. And therefore, rather than seeing this sine wave, which is made up of, in theory, the infinite odd harmonics, then you won't get a square wave. You will get something tending more towards the sinusoid with humps in it. And I'm going to try and demonstrate this as best I can to try and give you some idea of what's going on. So what I'm going to do is put my, go back to the scope. I'm going to put my probe on times 1. So let me just put my probe on times 1. And we are going to go to plus or minus 2 volts, and I'm going to put my signal generator on, and I'm going to put it started off at 100 kilohertz. Okay, and we're just going to bring the time base in so we can actually see this. There we go. So I want to change this to a square wave, so just bear with me again whilst I change the waveform to a square wave. So that's looking great. We've got a square wave there. So everything's fine at the moment. Because if we look at this from a frequency domain, we're only running at 100 kilohertz. So all the odd harmonics will be 300 kilohertz, 500 kilohertz, etc. And the scope probe is actually able to see those. But if I start to increase the frequency on this, so if I now go towards the 1 meg, I'm just going to, yes, we've got the frequency there. Let's keep on. Let's see, I'm just wondering which is best here. I'm going to do it in hundreds of kilohertz. So this is now 200 kilohertz, and I'm just going to open up the time base a bit. There we go. And you'll start to see this is the rounding effect, and going up to 400 kilohertz, 500 kilohertz, 600 kilohertz, 700 kilohertz, 800 kilohertz. We're starting to get into the bandwidth issues here, because this is a times 1 probe, 900 kilohertz, and you're seeing that it's no longer a square wave, it's actually more of this sort of like tending towards a sinusoid. And so if I keep on raising the frequency, and also we're now attenuating as well, and so we've lost our square wave. This has become more of a sine wave because we're fundamentally bandwidth limited by the actual probe itself. So I'm going to change this back to a times 10. I'm going to leave it on 1 megahertz for the time being. I'm going to change my scope probe to times 10. And let's go back into here, probe times 10, change this back to, whoops, 2, there we go. So now you see that because we've increased the bandwidth of the scope, now this was tending towards a sinusoid when you had it in times 1, but now it's actually back to a square wave, which is great, and at 1 megahertz. And now what I'm going to do is increase this and see what happens. I'm just going to open up the time base here and open up a bit more. There we go. And look, examine this. So we're on 3 megahertz now, 4 megahertz, 5. And I'm just going to increase the time base again. And you're starting to see this ringing as well, but also you'll start to see the formulation of these double peaks. And this is partially to do with the fact that we're getting the close harmonics. This is 16 megs. So if we times that by 3, then the next harmonic is 48. So 48 megahertz is the first odd harmonic. And so there's our fundamental at 16 megahertz. So the part of this frequency in here will be sitting at 48 megahertz. And as we actually increase this frequency more and more, then this is tending back towards a sine wave because of the limits of the bandwidth of our probe and our picoscope as well. So this is why you would expect to see a square wave, but no, the bandwidth is limiting the square wave, so we can't actually see it. So it doesn't mean to say there's not a square wave there. It's actually because the scope itself and the probe are actually limiting this, and therefore you end up with this type of waveform. And this goes to really just explain that why you've got to understand the limitations of the test equipment you've got if you're trying to observe particular types of signals. So let's go back to the PowerPoint presentation. So in conclusion, what can we say about everything we've just learned? So the first thing is, for the most accurate measuring within the limitations of the test equipment, make sure you zero your channel offsets on your picoscope, and also to null the electronics, and try and perform this on a regular basis, okay? Also do make sure you do frequency compensation, which is also very important, of which, remember, you can use the signal generator in the picoscope to perform that task. If you're measuring very low voltage signals, then from DC up to 100 kilohertz sort of thing, but less than probably at the lower end, about the 200 millivolts end, then put your probe on times 1, but just make sure that you do understand there's a frequency limit when you do that. So that's really where you're starting to use your times 1 probe. But otherwise, in all other conditions, use times 10. So if you're uncertain, use times 10, because you're going to get a better result that way. But if you've got very, very low signal and it's not particularly high frequency, then go to your times 1. So remember that all probes have both a resistance and a reactance, and therefore it will affect your circuit in terms of the way you're measuring it. So you could easily stop a whole circuit from working just because you've attached your signal, your oscilloscope, to a data line. Say, for example, you've got an address line you've connected to it and you're trying to monitor it. Well, you could actually kill the address so the whole system doesn't work. It's about understanding the limitations of what you're dealing with. This is not a problem when you're using a times 10 probe and your bus might be running at sort of like maybe, I don't know, 1 megahertz or 10 megahertz or something. But if you're trying to run something at, 100 megahertz, then you've got to make sure you've got the right test equipment to be able to perform that kind of task. And you may want very special types of probes to actually monitor that to see what's going on, okay? And remember that what you see is not necessarily what's actually happening because of the high frequencies, because remember, square waves are, and quite often we're looking at square waves, but square waves are made up of harmonics. And if your bandwidth isn't big enough, you can't see those harmonics, and therefore you'll end up not seeing what's really there. So make sure that your test equipment meets the requirement of what you're trying to monitor. And then finally, scope probe design is extremely complex, and there are probes that are designed for many specialist applications, and especially in the high frequency domain. And in general, these probes are hugely expensive. Yeah, if you're going to be monitoring 500 megahertz and that kind of stuff, then really your scope itself will probably be in the thousands of pounds. So, but the probe is a significant part of that cost. So just be aware of that. So I hope you've enjoyed this video, learned something from it, and I look forward to seeing you in the next video.